Hello everyone, very good evening one and all. Welcome to Wallah and welcome to the session. Dear friends, we were discussing about the arrays data structure in this series and we have discussed about array insertion, deletion, lower triangular matrix and upper triangular matrix, three-dimensional array, stack implementation using an array, simple queue implementation using an array, priority queue implementation using an array, right? And now we will be discussing the tree representation as an array. Hi Raj Sarkar, good evening. Everybody, please confirm, am I audible and visible properly or not? Am I audible and visible properly or not? Please confirm. All good, Divyansh, Raj Sarkar? Yeah, great. Thank you. Fine. So, in the last class, we have discussed about this priority queue. What is a priority queue? Priority queue is a special queue in which insertion deletion is done based on the priority. Insertion and deletion is performed based on the priority, which is additional parameter for every element along with the value. So, in the priority queue, every element will be having two properties, two parameters. One will be value, other will be priority, right? And this priority queue is used in binary heap implementation. In binary heap implementation. And this priority queue, when used in binary heap, we can say there are two types of priority queue as max priority queue or min priority queue. Max priority queue, min priority queue. In max priority queue, maximum element or bigger element will be given high priority, and in min priority queue, smaller value will be given more priority. That is the difference between these two, max priority and min priority. And then we have two implementations for either max priority or min priority. One is as ordered array or as unordered array. We can implement priority queue in either of two modes, one as an ordered array or as an unordered array. Hi Nishu, good evening. In the ordered array, whenever we are inserting the elements, we will make sure the elements in the array are in the order of priority. Henceforth, we may need to shift all the elements in the worst case. Hence, NQ operation takes linear time. And DQ operation as we are already maintaining or confirming or making sure the elements are in the order of priority, while NQ operation DQ is just one step away, like it takes constant time. Now, as unordered array if we implement, while NQ you need not to bother about the order of priority, hence it will take constant time, but while DQ operation, we will make sure the highest priority element is DQ'd first, for which you may need to traverse all the array. That's why it takes linear time, right? So this is what quickly I can say what we discussed in the last lecture. By chance you missed watching it, you can watch it later when you get free time, which is available in the playlist. Okay. Now, in today's lecture, we will be understanding what is a tree, the tree data structure. In this, we will be picking binary tree, because tree need not to be binary tree always. Yeah. No issue, Raj and Nishu. You can just check it later whenever you get free time. Okay? Yeah. Tree need not to be binary tree. It can be ternary tree also, or it can be multi-dimensional also. It can have n degree. So, n-ary tree also. So, if at all we are making sure the tree is binary tree, then how this binary tree is represented in an array. In this, we will be trying to understand the indices of parent and left child, right child, and how we actually maintain them in the array. Okay? Everyone, can we proceed ahead to discuss the same? Please confirm. Please confirm, guys. Raj, Nishu, Divyansh and everyone. Shall we go ahead for the discussion? Yes. Now, firstly, what is a tree? We know that data structures are basically classified into two types. Data structures are basically classified into two types, as linear and data structures and non-linear data structure, isn't it? Linear data structures and non-linear data structures. Under linear data structure, we got array, stack, queue and linked list. Under non-linear data structure, we got these trees, graphs, sets, tries you can say, maps you can say. Yeah. Now, tree, which is a non-linear data structure. So, tree comes under the category of non-linear. So, we can say the tree is a non-linear data structure Why we are calling it as non-linear? Because the data structures has the definition as representation of data, right? So, it is known as non-linear because the elements which we call as nodes, the elements or nodes are represented in hierarchical manner. In hierarchical manner. Excuse me. And inside the tree data structure, whenever we are representing the data in hierarchical manner, we should make sure the tree must not contain cycles in it. Cycle means closed loop. So, we have to make sure the tree is always open. So, we can say a tree is a cyclic graph. Yes, exactly. Tree is a cyclic graph. All right. Now, if we take the tree like this, suppose this is the tree we are taking, and you can label them as you wish. Let's say A, B, C, so on. I am labeling. Here we have multiple nodes or multiple elements in this list, and we are representing them in certain hierarchy. So, in this hierarchy, the topmost element is what we can call as root node. And you see in the hierarchy, there is a falling edge from one node to another node. The descendant edge is there, right? So the nodes which are descendant from other node, they are said to be children nodes, like children of A. Similarly, E, F, G, H have the descendant edge from B. So, these are children of B. Similarly, these are M and N are children of H, and so on and so on. Now, the nodes that are having the same parent, the nodes that are having the same parent, they are said to be siblings. They are said to be siblings. Like B, C, D are siblings, E, F, G, H are siblings, M, N are siblings, O, P are siblings, I, J are siblings, and so on. So, what are siblings? Which have the common parent, same parent, right? Now, in these nodes, guys, we can say there are two types of nodes. We can say there are two types of nodes. One is internal nodes, other is external nodes. Internal nodes, external nodes. No, Raj Sarkar. B, C, D are siblings to each other. B, C, D are children of A. A is the parent, B, C, D are children for A, and for each of these, like B is sibling to C and D, C is sibling to B and D, D is sibling to B and C. They are siblings to each other. Okay. Now, the nodes can be categorized into two types as internal nodes, external nodes. External nodes are also known as leaf nodes, and internal nodes are also known as non-leaf nodes. Leaf nodes, non-leaf nodes. Now, what is a leaf node? Leaf node is the one which has zero child. A node with zero children. That is what you can say as leaf node. So, here E, F, G, M, N, O, P, Q, R, I, these are all having no children, means there is no descendant edge, no falling edge from them. So, they are called leaf nodes or external nodes, while the other we call as non-leaf nodes, means nodes with one or more children. Nodes with one or more children. So, you can say non-leaf node means a node with minimum one child. With minimum one child. That means it can have even more also, but minimum one child should be there. We can call it as non-leaf. So, root node is also non-leaf node or internal node. Now, what is this root node? A node which has no parent. A node without parent. That node, such node we call as root node. Right? And now listen carefully. Listen carefully. Here, once we understand the terminology of parent to child, A is having 3 children, B is having 4 children, H is having 2 children, J 2, K 1 child, L 1 child, leaf nodes 0 child. So here all nodes are not having the same number of children, isn't it? All nodes in the tree are not having the same number of children. So how many children? The number of children, the number of children per node is what we call as degree of the node, is what we call as degree of the node. So here if I take the nodes, node and degree, A is having 3 child, B is having 4 child, C is having 2 child, D is having 2 child, E 0, F 0, G 0, H 2, I 0, J 2 child, K 1 child, L 1 child, M, N, O, P, Q and R, these are all having 0 child. So what is the degree of A means 3, degree of B 4, degree of C 2. So how many children are there for a node? That is what we say degree. Now what is the degree of a tree? Whole tree degree. Whole tree degree is what? Maximum of degrees of the nodes is degree of a tree. So max of all degrees is called degree of a tree. So what is the maximum of all this? 3, 4, 2, 0, 1, 4. Hence, what is the degree of this example tree? 4. So degree of the tree is equal to 4. Got it? Everyone? Hello, 𝐂𝐤𝐧𝐤𝐬 CSC. I forgot your name. I think you are Shankar. Very good evening. Everyone understood? Okay. Now, dear friends, when we are representing in array, whenever we are representing in an array, so let us consider the tree representation as an array. Let us consider first one example tree. Okay, before this, we have to take binary tree. I am not going to take for any tree with any degree. First, I would like to only talk about binary tree. So, what is binary tree? A tree with or whose degree, is equal to 2. tree degree, I am talking, not node degree, tree degree is equal to 2. What will be the tree degree? Maximum degree. Maximum degree, right? So, what does that mean? We can define binary tree also as a tree in which the maximum number of children, that means a degree per node, degree of the node is 2. That means a node can have how many child? A node can have either 0 child or 1 child or 2 children. Maximum is 2. Right? So now, if we take example of binary tree, first is a node with a tree with only one node. Is this a binary tree? What is the degree? Degree is 0. But a tree whose degree is equal to 2 is binary tree? No. So here this definition should be corrected. A tree whose degree is less than or equal to 2. Not always equal to 2. Less than or equal to 2, because it can be less than that. Degree of a tree can be 1 also, 0 also, 2 also. So definitely, is this a binary tree? Means yes. Because what is the degree? 0. Okay. Is this a binary tree? What is the degree of this? Like let's say these are A, B. What is the degree of A? 1. Degree of B? 0. What is the degree of tree? Degree of tree, max of 0, 1, 1. So definitely it is binary tree. Is this a binary tree? Just take the degrees. Degree of A is equal to 2. Degree of E is equal to 1. Degree of B equal to 2. Degree of C equal to 0. D equal to 0. F equal to 0. Then what would be the degree of tree? Maximum of all these degrees, 2, 2, 1, 0, 0, 0, which is equal to 2. Yes, the tree degree can be less than or equal to 2. So definitely it is a binary tree. And at last, let me take one example. Suppose this is the tree I am taking. Is this a binary tree? Is this a binary tree? Just check the degrees. Just check out the degrees. Degree of A is 2. Degree of B is 0. Degree of C is 2. Degree of D is 0. Degree of E is 3. F 0. G0 H0. Now, what is the degree of a tree? Degree of a tree. Maximum of degrees of all the nodes, which is max of 2 0 2 0 3 0 0 0, which is equal to 3. It is not less than or equal to 2. Hence, it is not a binary tree. It is not a binary tree. So, everyone understood what is the meaning of binary tree? Please confirm. Everyone got the point? What is binary tree or what is not binary tree? Okay, great. Now, binary tree representation as an array. So, let us have an example of binary tree as suppose A, B, C, D, E, F and G. Is this a binary tree? You can check. The degrees are 2, 2, 2 zeros. Yes, definitely it is a binary tree. Now, if we want to represent this in the form of array, what we have to do is, we have to declare an array of size 2n plus 1. Declare an array of size 2n plus 1 where n is total number of nodes. Where n is total number of nodes in binary tree. Let the array be tree. Let the array be tree. So, what would be the size of an array now? How many elements are there? Number of elements. In this example, number of elements comma n is equal to count 1, 2, 3, 4, 5, 6, 7. Now, what is 2n plus 1? 2 into 7 plus 1, that is 15. So, we have to take the tree size as 15. So, declare an array of size 15. Done? Now, I am taking the array. With indices with the size 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. Right? Now, what we have to do to represent in the form of array means, first label the numbers label the numbers for the nodes in the top to bottom, left to right order, which is called breadth first sequence, starting from 0. So A will get the label 0, B1, C2, D3, E4, F5, G6. Okay? And these are what we call as indices, where those elements are supposed to be stored. So we are taking the array with the default indexing, so from 0, 15 size we have taken, so indexing would be from 0 to 14. Now at 0th index what is there? A. At 1 index what is there? B, C, D, E, F, G. Then what about the rest? They are all empty, you can say, or you can say null. You can say empty or null. That is based on our implementation, how we implement, that is purely up to us. Null is a predefined constant, guys, so we can define it with null also, right? \0 is a predefined character, null character. That is okay. Like you want to take it as a string array, if you want to take it as a character array, then you can say it is \0. You want to take it as a number array, then you can assign with the predefined constant null. Okay? It purely depends on our implementation. You can use \0 also for character array. Okay? Now, as you see here, every node is having 2 child except leaf node. Here, where we got the blank at the end, later we may trim this array and we can actually utilize the space effectively. Right? Now, before we move to another example, here if you look at, A is the parent node, isn't it? A is the parent node. And A left child is B. A left child is B. And A right child is C. A right child is C. Now, when the parent node index is 0, its left child index is what? 1. Its right child index is what? 2. So, when the parent node index is 0, its left child is at 1, its right child is at 2. Right? Okay, let it be. Now, when B is the parent, B left child is D. B left child is D. And B right child is E. So E is the right child. So right of E, right of B. When parent node is at index 1, its left child is at index 3, its right child is at index 4. Right? So, you can understand some relation, some relativity here. In the same way, if I take C as the parent, C left child is F, C right child is G. So if the parent is at index 2, its left is at index 5, its right is at index 6, right? So from this we can say, if parent node index is I in an array, then its left child index would be what? 0, 1, 1, 3, 2, 5. So you can say 2i plus 1, 2 into I plus 1. So that 2 into 0, 0 plus 1, 1. 2 into 1, 2 plus 1, 3. 2 into 2, 4 plus 1, 5. It's satisfied for all. Similarly, what would be the right child index? Two multiplied by I plus 2. So 0 into 2, 0 plus 2, 2. 1 into 2, 2 plus 2, 4. Right child of B is at 4. C right child, C is at index 2. 2i, 4 plus 2, 6. C right child is at 6. So it's satisfied. So if parent node index is known, then its left child index and right child index we can compute in this way. Or else we can say, if child index is known to us, like if child index is, let's say, some x, then its parent index will be what? X minus 1 by 2 seal value. What is this? Floor value. Floor of x minus 1 by 2. You can see, like one child G index is 6. So where would be its parent? 6 minus 1, 5 by 2, some 2.5, but when you take the floor it is 2. So 6 parent will be at index 2, in that way, right? So if parent index is known, its left and right child indices can be found. If child index is known, as because there will be only one parent, any child index, it may be left child or right child, any child index is known, then you can easily find out its parent index. Do you people understand this? This is very, very important in the array representation for a binary tree. Right. Now, with one example, we will conclude with another example. Suppose I am taking a binary tree like this: A, B, C, D, E, F, G, H. I. Now, what should be the array size we have to take? First you tell me. This is the binary tree we got. What should be the array size we have to take? Array size must be 2n plus 1. How many nodes in the binary tree? 1, 2, 3, 4, 5, 6, 7, 8, 9. So, n is equal to 9. That means array size you have to take is 2 into 9, 18 plus 1, 19. Now, let us take the array with 19 size. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 and 19, and the indices would be from 0 to 18 only. Now, root index will be always 0. Root node index will be always 0. So, at 0th index A will be stored. When root node, when a parent index is I, 2i plus 1 will be left child index, 2i plus 2 will be right child index, right? So, at 1, A left child B will be stored, at 2, A right child C will be stored. Now, take parent as B. Parent index is 1. Its left child will be at 2i plus 1, 3. And its right child should be at 2i plus 2, but there is no right child, you have to make it null or leave empty, okay, whatever we want, just for the representation sake. Now, go for C. C is the parent, like we have taken A and B. Now take C. C is the parent. At 5C left child must be there is no left child for C. At 6C right child must be there, so here we got E. Now D. D left child must be at 2 3s are 6 plus 1, 7, and right child must be at 6 plus 2, 8. Now, next element we have non-zero element or non-null element is at 6. So, if the parent is at 6, its left child, if at all there, it should be at 13 index. It should be at 13 index. 2 6s are 12 plus 1, 13. So, does E has left child? Yes. So, here you have H. The next non-zero element is F. So, at 15 index, we should have F left child, but we don't have F left child. At 16 index, we should have F right child. Now, G left child, right child, no. So, all the other we have to make null or leave empty. You got it now? So, in the array, we represent the tree like this, binary tree. Did you get it, guys? That is the reason why you have to take 2n plus 1 array. Nishu, hope you understood now why we are taking 2n plus 1 size array. Because every node may not have 2 child like previous example, no? But still we have to leave the space or memory for its respective index. Then only that 2i plus 1, 2i plus 2, that positioning will work. Right? Great. So that's all guys for today. So today we understood what is, first of all, what is a tree, which is a non-linear data structure, and what is the some terminology that is related useful for us, like maybe what is a parent, what is children, what is a sibling, what is root, what is leaf node or internal node, external node, and we have also understood what is the degree of a node and tree, which is number of children per node is degree, maximum degrees is degree of the tree. And then we understood what is binary tree and binary tree representation as array. Right? So this is what these are all what the key takeaways from today's class, dear friends. Hope every concept that we discussed in today's lecture is clear for you. Let us meet in the next lecture. Tomorrow don't miss the class, because tomorrow we are going to have practice session. I'll keep gate questions and gate level questions tomorrow. So let us practice on these arrays, data structure tomorrow. Okay, don't miss tomorrow's class, sharp at 7 p.m. Till then, have a great time. Thank you so much for joining the session, guys. Keep attending the lectures regularly. Keep learning, keep growing. See you tomorrow. Good night. Bye-bye. Jai Hind.